My name is Velda Kiara. I am a software engineer. I sit on the Django Events Foundation North America board, which is responsible for DjangoCon US. I am a Microsoft Most Valuable Professional for Python, renewed for the second year, so that's great. And I also recently became a Python Software Foundation Fellow. I run a newsletter called Storytellers by Tales on Substack under veldakiara.substack.com. I help maintain Django Debug Toolbar. If you've used it, I helped create some of the features. And I also contribute to other open source projects, specifically in Django. And I write technical articles, specifically also heavily related to Django. I've written for FreeCodeCamp and dev.to as well. And I am part of the Djangonaut space as a star, where I contribute to the Django news updates, specifically to update you about what's going on with Django. So early in my career, while I was looking for an attachment, I was in my undergraduate program in my third year. I got to have the privilege of having a friend who had a startup company, and I got of course, I brazed through the interviews, and I was able to become an attaché there, where I actually got to work on actual projects. So I was fairly new because I was also exploring what I could do with Python, whether go into web, whether do a lot more about data and all that. So I learned about Django during the attachment, and it helped me realize that, oh, I could actually build things faster. Like I could have features with the add-on of the admin interface out of the box. And it still keeps everything in Python. And I also learned about the ORM because Django comes with its own ORM. And I realized that, the tools are just tools. Like they can also cause problems if you don't understand what's going on underneath. So the reason why I care deeply about this topic is I performed SQL queries. So I joined 4 tables. And the tables had users and orders and products, which is what I was working on at the moment. And apparently the person who gave me GitHub access might have given me too much because I was very audacious. I merged everything and I was like, yeah, I was feeling very confident, feeling very good about what I had built. And then when it came to staging, I had a Cartesian explosion, so nothing was working. I had to receive not very fun calls, and some access was revoked, but I was still like, oh, that can actually happen. I was excited and nervous. I was like, so have I lost my attachment? Should I start telling my university to give me more time because this is done? They're like, no, it happens. And the mistake was on both sides because whoever gave me access also gave me merging access. Who does that? I just joined. Bam, do better. So the reason I also care more about this is because as developers, sometimes we might struggle with databases, and not because we don't understand it, it's because we haven't really dug into what's happening in the background. And it's not just understanding how data is fetched, but how do you actually model data, what's going on in the background. And there's always the choice of why we do things in one way or rather in another. And there are always choices and trade-offs, as we like to say. And there's reasons behind why things are done in a certain way, right? So how I fixed the Cartesian explosion, because they held me responsible and I had to account for my actions and fix my mistakes. They gave me, I had to go through documentation and realize, oh, there's also prefetch related and select related. And I was like, ooh, I didn't know about this. So I got to also do that and implement, and it was also a learning opportunity for me. Not so much for them, but I learned something. So in this talk, I want to take you through that same journey, from writing raw SQL to ORMs and then into the middle ground and how everything works together. But to do this, we need to start from the beginning. So SQL, which is structured query language, has been around since the 1970s, and it was designed to let people interact with structured data stored in relational databases using simple declarative commands. So, I mean, despite its big age, it's still like it's the still dominant language for managing data for small applications and for big applications. And the reason why it still endures is because most relational databases support it, like Postgres, there is Oracle, there's MySQL, they support it. And it's also declarative in that you say what you want, but not how to get it. And it's also flexible, powerful, and mature. And a lot of people in this room have already worked with SQL. So raise your hand if in any project that you've ever had, you look at either the users table to just see what's going on. Select star users. Yeah, I mean, who doesn't want to know what's going on? So I also do that almost every time because I want to see, despite using an ORM, I want to see what exactly is going on. So this particular art that you're looking at, not my best work, but it works. It's a Lego presentation of a house. And imagine your app is probably not a Lego house, but an actual house. And the SQL is basically the material used to build it. So it's basically like bricks. So each query is like a brick because it's small, it's functional, and it's reusable. And if you put bricks together, they can form walls, which are your tables. And the rooms, whether it's your dining room or your bedroom, become the schema, and the actual building becomes your app. So a solid house depends on a well-structured foundation. And that's similar to how apps rely on performance and reliability, because all this performance and reliability is based off on how data is actually organized and accessed. So SQL organizes the data into tables with rows and columns. So the tables are objects like user table, orders, and the rows are the individual records that you have. The columns are like fields, like an order or a user has a name, has an email, and an order has a price and an order number. And that's how everything works together. And then the relationships are now the foreign keys of how the actual data links together, which is the relational structure. So common SQL operations, we all know this, it's select, insert, update, and delete. So select just reads data, inserts, adds data that you'd like to add, and then updates modifies existing data, and delete just removes the data. So this is an example of how we would use the separate commands. So in this particular command, the first command is to be able to get all the users. If you want to add users, say name and email, you have to pass in those fields and then pass in the actual values that you want. And if you want to mark inactive users as for the beginning of 2024, you could update the users as well. And if you want to delete users, depending on the interval you want, whether it's 30 days to a year, whatever timeline that works for you, you could do that. So what I'd like to mention here is that, we do have insert and update and delete, but this is also similar to what ORMs use, like the .save function or the .filter function. So that's still SQL under the hood. It's just that you haven't interacted with SQL at that level, but you're just interacting with SQL. So a couple of use cases where you majorly use SQL as well is in transactional systems where accuracy matters, specifically in banks, like when you're withdrawing or depositing money, you don't want to have discrepancies in your transactions. Like you still want to have the same amount of money that you had and not have more than you expect, right? And it also in terms of e-commerce, when you're creating an order, you also want it to deduct from inventory. Otherwise, the user will end up having an order that is not existing because we don't know what's going on in inventory. And then SQL ensures ACID, which is atomicity, consistency, isolation, and durability. So atomicity, because a transaction is completed entirely or not at all, and consistency in that data moves from one valid state to another following the rules and constraints. Isolation in that if there are concurrent transactions, they act as if they're the only one, so it prevents interference. Durability in that once done is always done, and that's how it can survive system failures. The other use case is in reporting and business intelligence, telling us, okay, what is going on? How many sales did we make? How many users signed up? And all that information. And in terms of also data warehousing, so SQL is not used just for small apps. It's also used in big data pipelines where you have batch processing and analytics like in companies like Snowflake. So SQL isn't outdated. It scales to everything from like small apps, you want to start your own startup, or for billion-dollar companies. So as I said, SQL is like a pile of bricks, but you can build everything. But you also need to have the time and the skill because it does take a lot of time. So the intent I have with this code that you're looking at is I want to get the names and the emails of active users. But to do this, if I'm doing this in SQL, I'll start by opening up the connection, writing the SQL by hand, which is verbatim, and then I also have to fetch the same result. And possibly, if I want to pass it in Python objects, I'll also have to do that too. So the first pain point is that there is a lot of verbosity, like a simple intent or idea takes 6+ lines of boilerplate code. And imagine if you have to repeat this particular pattern across every view, every API endpoint you have for your application. It becomes tiring and it's also error prone. So there is also the question of security because this particular code you're looking at, it fetches the user ID from the URL and it constructs a raw SQL query by inserting that value directly into the SQL string, which creates some drama, as I say, because there's a risk of SQL injection because if somebody has a malicious input, as you can see, this particular code will return all the users. And let's say you are also storing credit card information. That's how people get access to people's credit card information, which is not good for anybody. And the other point is there are turnarounds to this, like you can easily combat or mitigate this, but it's not intuitive. Like it's easy to forget, and even if your team knows about parameterized queries, the moment you forget or cut corners, you're open to attacks. And this particular pain point is you have to remember to sanitize everything yourself. And it creates nightmares. Nobody wants to have nightmares. You all want to have sweet dreams. Like, for example, if you want to actually add a new field, let's say username, right? And you're writing this, and you have hard-coded this in your SQL, and you have like 40 or 50 files. You'd have to go into each file, update that, and add the username. So each update that you'll have to do will involve a lot of testing, a lot of validation. And if you're copy and pasting, there's some errors that may also happen because humans are not perfect. So schema changes will result to application changes, which are not so great. So it's not so easy to define. But if you're using an ORM, you just define the model once, and once your schema changes are all localized, don't have to worry about trying to syncing all the different files because queries are updated automatically. So we can be delusional for a minute and say, maybe the biggest pain point isn't code. Maybe it's the actual mindset. It's just because we were thinking it's hard. But SQL thinks in rows and columns, and trying to map like Python to SQL with this there's a lot of context switching involved because objects can have methods and they can have relationships and other computed properties. So the constant switching and having to like nest, if your data is actually nested, can also have, can cause a little bit of confusion because you have to like pivot for, is it SQL, is it Python, what am I writing? And this causes like an impedance mismatch because of the context switching. So you have to keep converting back and forth. So a good example to compare how you would do this in Python to be able to get a post object or accessing the related object for the author or get the comments for the blog post, this is how you do it in Python. And this is the same way you would do it in SQL. And the reason why it hurts is that the same intent uses more lines of code. That is, you're writing a lot more code, which with less meaning. Like, we could do this and be done with it, but in SQL, you have to do all this. So what if we could still stay in Python and still work with our database, but in a more cleaner, safer, and Pythonic way? So this is where ORMs come in, which are object relational mappers. So they act as a bridge between Python's world of objects and SQL's world of tables. So an ORM is basically like a translator. It speaks SQL to the database, and it speaks Python to you. And SQL uses the tables. What we regard as tables are actually Python classes or other models. The rows are the objects. The columns are the class attributes, and the select/insert are the methods that we do, like the save function and the filter function. So based on this is how we would do it with an ORM. Like, based on this, you can actually see that we're trying to achieve the same result, getting the active users. We're getting the same result. We're having a clear intent. There is also less risk, and it's easier to test and maintain as well. So a couple of benefits of the ORM is that you don't write SQL manually. So it abstracts that layer for you. You describe your data models, and the ORM handles the query generation. There is also reusability in that ORM models are just Python classes. You can inherit from base models, you can add custom methods, and you could also reuse this across views, APIs, and CLI scripts. There is also some form of safety in that ORMs automatically sanitize inputs to prevent SQL injection. So there is less surface area for security mistakes. In terms of maintainability, all the schema changes are handled in one place because migrations let you evolve your database as you evolve your app. Now that we know what ORMs do, let's take a look at the history of ORMs. So before ORMs is now where we're living, having to write SQL, performing manual query strings, having manual schemas, and there wasn't any particular standard way to handle database access in code, and every app reinvented the same boilerplate, which is what we just discussed. The second part is the first layer of abstraction, which involved Active Record and Django ORM. So Ruby on Rails in 2004, it published Active Record, which was one of the first mainstream ORMs, where each database table was directly tied to a class. If you had users, that would be mapped to the users table. And they popularized the terminology of like convention over configuration. And then Django ORM, which was formed in 2005. Shout out to Django, we're celebrating 20 years. And it brought the similar ideas to Python, but it focused on declarative methods, reusable query interfaces, and of course, built-in admin interface. Like, I don't have to go and code it out on the first try. Like, if I want to do something very fast, I could do that. And it also, the Django ORM also helped have the principle of do not repeat yourself. That is, you define the structure once, and then you use it everywhere. So part 3 of this also evolved from SQL Alchemy and the rise of flexibility. So SQL Alchemy in 2006 offered more granular control as compared to Django ORM, and it did this with 2 layers. There is the core, which was the SQL expression language, and the ORM, which was optional but was powerful to use. So it emphasized the convention of explicit over implicit, where it was ideal for developers who wanted to actually write SQL on the background when they needed to. So it was a big shift in that ORMs never really now hid SQL entirely. They empowered the structured interactions with the option of, like, if you want to write SQL, you could. So where we're at now is where we're in async and using modern use cases. So as Python has adopted async in the way, new async ORMs also emerged, like Tortoise ORM, Geno, and SQL model. So we also have other frameworks which are optimized for the web, like Fast API and Starlet, and asynchronous ORMs too. They enable you to have concurrent database access. There's faster API responses and better scalability. So they started to become preferred. So instead of having to string together SQL queries, you could just describe it once in your data and let the ORM do its job. So now that we know how ORMs came to be, let's take a look at some of the popular ones today and how to choose the right one for your job. And the beauty, before I show that on ORMs, is that once you know how to use one ORM, it's easy to use another because it's just syntax changes and the intent is still the same. Like if you're using users that get something, you'll have to filter with is active or is not active and the username that you want. So first of all, just because you can doesn't mean you should. So you also need to learn how to choose the right ORM for the right job that you have. So Django ORM is ideal for Django applications. It has seamless integrations with admin, forms, and views. And schema changes with like make migrations and migrate command help you make the schema changes. And there's also like a reach query set API for like chaining filters and lookups. SQL Alchemy is ideal for complex or dynamic schemas and hybrid flows. It offers both ORM and SQL expression language. It's powerful for database-first projects or where you need fine-grained control over SQL. Peewee is minimalistic, and it's easy to use and great for small apps or scripts that you'd like to run. It's also ideal for prototyping, CLI tools, or embedded systems. Tortoise ORM was built for async I/O from the ground up. It's perfect for Fast API and asynchronous services. The reason why it's preferred is because it also has almost the same style as Django for the models, and it's great for streaming, or running concurrent applications. SQL model combines Pydantic validation and SQL Alchemy ORM, so where models can be reused for both databases operations and request/response schemas. So these are some of the ORMs that are there. There are definitely other custom ORMs, but this is the scope that we're having right now. So the intent we have is to be able to get all active users with the email having example.com. So this is how you would do it in Django ORM. As I said, you have to filter to see the actual user if they're active and if the email actually contains what we're looking for. This is how you would also do it in SQL Alchemy. And SQL Alchemy is flexible because it works with nearly any framework. And common frameworks that use this are like Flask, Fast API, Starlet. And the reason why it fits is because it's decoupled, it's powerful, and it's also adaptable. Peewee is more of a lightweight ORM, which is ideal for minimalistic frameworks or no framework at all. And perfect pairings are like Flask, Bottle, if you've heard of it, and Falcon too. And the reason it fits is there's low overhead and it's easy to embed as well. So this is Tortoise. Has anybody used Tortoise in the room? Falcon? Wow, so I'm not the only one. I tested it out, but it didn't work. So this is still the same intent, but it pairs first with fast API because it was also designed for asynchronous services. And the reason it fits is because of asynchronous functions, and it's also clean. It has a clean API, and it's also Django-like in a way. So SQL model was designed by the creator of Fast API, so it definitely fits with Fast API if you'd like to use that. It also integrates with Starlet, and the reason this works together is because it uses Pydantic validation with SQL Alchemy, which is perfect for modern APIs. And of course, ORMs are not always the right answer, so let's talk about when you actually might want to write SQL. So where ORMs shine is specifically when most of your work involves a lot of CRUD, like creating, retrieving, updating, and deleting records. The other part is if you want to build out features quickly without worrying about SQL syntax, it handles the grunt work for you. The other part is that it's also easy to tie your Python classes to logic directly to the database structure that you have, which is good for fast-moving teams or companies. So for example, if you had a startup and you're like, okay, let's see what I want to do. I want this off the ground to be able to present it to people who want to actually buy your product or sponsor the development of your actual application. You could do this with Django because it has model validation, it has the built-in admin interface, and the views and schemas and migrations are all out of the box. So when raw SQL now starts to win is when you have complex joins or subqueries where if you have like deep report styled guides, especially with like nested aggregations or CTEs, which are common table expressions. The other part where SQL really shines is when you need full control over indexes, query plans, or advanced PostgreSQL features, or PostgreSQL or PostSQL, whatever you want to call it. And then it's also faster when you want to do a lot of like batch work for your data. For example, if you have a dashboard, a reporting dashboard that needs materialized views and a couple of lateral joins, you would want to use SQL because it's cleaner and it's faster than an ORM workaround. So they can actually work together. You don't have to choose one or the other. It just depends with what you want to do. And the thing I would say here is that know what you're building and choose that. Nothing is ever either or. It could be both. As long as you know your terrain, you could easily understand, okay, this is where I can actually use Django ORM, but if maybe using an ORM here is actually overkill as compared to doing SQL. So as long as other ORMs heavily emphasize with using it, there are also fallbacks. Like I know Django ORM still allows for SQL fallbacks. And most real code bases actually use both. You don't have to choose either. So a couple of tips for teams is that you could use ORM for standard queries and domain modeling, but if you need to write SQL for performance-heavy or maybe non-standard edge cases, also document this so that people in your team could understand, okay, this way is faster if you're looking for this particular data. And don't fear mixing, just do both as long as it works. Like there is no ideal situation. All these platforms also have their own diverse weaknesses, and to compensate for this is to just try to use one for what it's best for. So a couple of takeaways that I have for you today is ORMs abstract complexity, and they speed up development, but you also need to understand what's going on in the background because they're just tools, and tools can cause problems if you don't understand what's going on in the background. And of course, SQL gives you more control, but it comes with a lot more responsibility. And as Uncle Ben says, with more power comes more responsibility. So you could use both, understand when to reach for one and when to reach for the other. And having this particular balance is not only cleaner, but more maintainable, and it's easy to also iterate faster. and performance issues always will be there, so find a workaround to also do that better. So that is it for my talk. I would like to thank you. I don't know if you have time for questions, or am I on time?